Viewers take note, this video is going to have a lot of technical information in it and a lot of talking in regards to the leading link, geometry of the steering of a leading link, and things like that. So if it's not your cup of tea, feel free to skip and watch something else and wait for part 2, because that's going to have a lot of machining and a lot of other hands-on stuff. So if you like this kind of stuff, stick around and I think you'll enjoy it. Howdy guys, welcome back to the channel. As you can see, I got the sidecar rig back up on the 2 lifts because we're going to be dealing with some stuff in this video that's really been bothering me that really needs to be taken care of. It's going to kind of be a number of different things. I'm going to go over some stuff on the leading link front end that I think you might be interested in. Let's go ahead and get to the sidecar here. I'll show you what we're going to do and talk about some things that you might be interested in that I've been asked about in regards to the front end of this sidecar. All right, we'll go over a couple of terminology things here. In regards to motorcycle, you have, in the front end that is, you have rake and you have trail. Rake is the angle of the front forks, if you will. In this case, pretend that there's forks sticking out down here. And trail is the distance between the center of the steering head, where it meets the ground, in this case, a flat surface, measured to the center of the tire, or the center of the axle rather, where the tire hits the ground. Now I'll show you in this picture here, which is from Cycle World, sportrider.com. They used it in an article. And so you can see right here, rake is this angle right here, which is the angle of the forks. And then you have trail, which is down here. So when you go straight down the steering head, right here, that red line, not down the forks, but down the steering head, that's where it pivots. And you hit the ground, that's where that mark is. And then the center of the axle, which is also conveniently the center of the tire, the high spot of the tire, that is your trail right here. Now in a typical sport bike, something like that, you have a much greater amount of trail. In other words, the tire is further back from that line where it meets down here from the center of the steering head than it would be like on a cruiser or other bikes like that. This is probably an oversimplified example, but we'll go ahead and use this caster as a visual aid. Now I'll kind of explain what I'm talking about here in regards to the rake and trail and how they apply to the sidecar rig. All right, so let's take this caster and put it over here. We're going to use this as an example of like a front wheel on a motorcycle. So pretend that the 2 sides to the caster are the ends of the forks that come down to it. And of course, in this position, it's offset forward to the swivel location. We'll pretend that's essentially the forks or the center of the triple tree coming down and then attaching to the forks themselves. So this is the triple tree and these are the forks down here, the sides. So first we'll look at it from like a sport bike perspective. That's a hard word to say in the morning. So if we take this, and you can see this is kind of lined up here down to that forward line. So it's straight down toward where the end of the triple tree center would land. And of course we have this lined up to the mark on the paper where the tire would land. So that's positive trail, and this is typical to a sport bike. The factors that run a sport bike compared to a cruiser or certainly a sidecar rig is lean. That is the main factor right there. And we'll get back to lean here in a second. Now in a sport bike, we want to be able to flick it over back and forth, and we want to be able to lean it. And you can see how easy that is to do. We're still pointed toward that line in which the center of the steering head is, as far as that location. And you can see this thing flicks back and forth real easy doing this. And in this case, you know, I don't really know the geometry that fluently, but as far as this goes, you're kind of tucking that wheel back further in relationship to almost, I don't want to say on top of the handlebars, but you're much closer to to that perspective than you are if it's flipped around, for example, like this, which we're going to get to now. So in this situation, you can see that if we put this line about in the center there, this is kind of exaggerated, of course, where it's pointing at the front line, at least pretty close, our wheel's much further forward. And in this case, it's very difficult to do what I just did with this thing, to kind of flick it around and make the thing fall over to the side, because that's what you have to do when you lean a bike. You flick it and the bike has to essentially fall over to the side. You do not want that to happen because it's very unstable when you're in a three-wheeled application like a sidecar, because the third wheel will not let the thing move left and right like a lean, and it wants to do that. So in this particular steering geometry, it wants to lean. This front end is designed to make the thing lean and be very agile, and is very sensitive to steering inputs. So you do not want sensitivity in steering inputs in a sidecar, because you cannot take advantage of those steering inputs because of the third wheel. So in this case, we push it this way, and again, you can get a pretty clear depiction of how this thing works when it's set up in a forward position. So it's much more stable for a three-wheeled operation, because generally speaking, you don't really ride a sidecar rig, you drive a sidecar rig. Just like you drive a car or a pickup truck or a tractor trailer, you ride a motorcycle, but essentially you steer or drive a sidecar rig, because it does not lean. So it's essentially doing the same thing that you'd have it do if you had a steering box and four wheels, two front steering wheels, whether it's your lawnmower or your Dodge Ram or Ford F-150 with the aluminum body that melts in high temperature, that sort of thing. This is the same kind of thing. You have this kind of steering for that kind of stability. So that's essentially kind of a Reader's Digest version, and also a little bit of a show and tell to give you a better perspective on why it's important to have a reduction in trail from this setting here, which flicks around really well and is very unstable unless the bike can move, and take advantage of that sensitivity, to something like this where it pushes up closer to that line and becomes much more stable. Kind of like a chopper. If you brought it way out here and leaned it way down, the thing wouldn't turn for crap, but it would go straight, really, really stable. So that's just an example of how this works, and my rudimentary explanation of thus. You know, another example would be one of those kids' push scooters, the two-wheeled scooters that has the steering directly above the wheel, just goes straight down through the platform of the scooter, directly down to that wheel, and that's how they steer it. In that case, you'd have zero rake and zero trail. Essentially, they have no geometry to be able to steer reliably, because there's no trail and no rake. You have to have a certain amount of rake and a certain amount of trail for it to be inherently stable, depending on what the design of the chassis is. So in a sport bike, we have more trail. In other words, it's further away backwards, it's positive trail to that line where the center of the steering head goes. And on a sidecar rig or certain cruisers and trikes and so forth, we reduce the trail and head toward that line, but we don't want to necessarily get to the line or certainly go negative, because it becomes even more unstable in certain applications. Take a chopper, for example, with really long front end. That thing would probably go straight pretty well, but the first time you try to turn it, the damn thing's about to flip over. So there is a limit on each side, and but the thing is, if you have zero rake and zero trail, that's really a no bueno. So it's just an example of the other side of the coin when it comes to this. In a sidecar like this, the whole purpose of a leading link setup, or some type of modifications to the forks themselves, where they articulate with the front wheel. DMC sidecars, now Texas Sidecars, does a really good job with that, where they actually, I'll see if I can find some photos of it, where they actually laser cut plates that go on the forks, and then the brakes mount to it, and it pushes the wheel forward, and the axle goes through a new spot on that. In this case, I didn't do that because I didn't know about that, and I don't have a freaking water jet. I built a leading link setup. What the objective is in a leading link setup, and we want to bring our tire, the center of the tire, closer to it. Now, I can't exactly tell you what that is, but generally speaking, it's about 2.5 inches, something like that. I only have 1.5 inches on mine because I kind of guessed when I did it. I really wish I had 2 inches. So in other words, if I put a pipe, and I had a pipe at that time, that would go straight down the steering head and fit inside here snugly, come straight through, and with nothing in the way, you could run it down the ground and make a mark. then you can start your setup and see where you're actually going to fall in when I started to build all this monstrosity here. I calculated it out to be about here is where the axle would be if it was on the forks, and I pushed it out to that far. Now it doesn't seem like a lot, but it does help tremendously to move that out. So it's in concert with the rake. The trail has an impact on making it easier to steer for a three-wheeled vehicle and certain other types of vehicles too. So that's basically that's the real basics of the leading link front end and why you do it as far as reducing the trail. So with that in mind, you can see how I built mine, which basically looks like it came out of the dark ages. And that's one of the things I want to address in this video. I want to do some better work on this because there's a couple of things I really don't like with it. Not in this order, but one thing I want to fix on this is this abomination on the side here is just something I did. There's a reason for it. Because I made this where it pinches down like they do on a lot of other bikes with regular forks onto the axle, there was no way to register the axle related to this part. On a motorcycle with regular forks, sometimes there's a little shoulder or something like that where it registers to it, or it registers to it exclusively on this side. So let's say, see I have the bolt welded inside here for the thread of the axle. Well, on a lot of bikes, what it does, it'll register over here and it's calculated in, so this falls exactly where it's supposed to be relative to the spacer inside there. Now why that's important is because of the calipers. When I built this, you have to make sure that the calipers are essentially centered on the rotors. So, and I don't really like this left one because what I did was, I did this one first, I remember. I put this thing in place, getting ready to weld it, and I essentially tied the brakes so it's putting the brakes on and squeezing the rotor, that way it self-aligns, and then I welded it. Well, this one I forgot to do that. And this one is dragged and squeaked the entire time, and I hate it. So I think we're going to end up cutting this off and redoing this. But we're also going to go in here and probably fabricate a new axle because this is a pain in the ass. I want something that'll shoulder up on the outside when that thing's tightened up, and that way I don't have to worry about alignment with some sort of a goofy gizmo on the outside that captures the end of that axle. So let me take that off first and I'll show you what it looks like. It works. But again, you know, I didn't have any machine tools or anything back then, so I just banged this together. It looks like shit, but it does work. I mean, this is about the damn goofiest thing ever. It really is goofy, but it does serve a purpose. There's a thread, like a little stud, that goes into the end of the axle that I drilled and tapped in. And again, I did it all freehand because I didn't have a lathe or anything back then. A couple washers, and all it does, again, sets the distance from essentially the edge of this to the end of the axle. There's a shoulder on the axle that goes up against the spacer that's all pulls together. So it tightens up on the right side here, that side over there, and pulls it together. There's nothing that'll keep this from kind of moving because it is kind of a leading link thing. And that brings us to another problem is back there, these where these bolts go through, that's really sloppy back there. And I accommodated for that by putting like thin washers. So not only is it the hole that keeps it in, but the sides keep it aligned. That's not the way to do it. I want to redo those too. I want to take those out on both sides and maybe even pull the entire forks out most likely and bring them over and remachine those to a little larger size and then put something through so they're a tighter fit. So I just want to do that a lot better. But we'll start at the end here. I figure while I have this all off, I'm going to put tires on it because the front tire is not so bad, but the rear is pretty bad. And I'm just going to shotgun them both because I got them in stock and I'm sick of kicking them around. So you see, I mean, this is terrible. I mean, it's just so freaking hokey. It's just ridiculous. But all it does is set that distance between here, and that bolt going through it captures that. So it pinches it here, and that secures to there. So it secures to the actual arm, and it keeps that aligned up so it only goes so, it'll only be in a certain amount of stick out, in other words. So the stick out from here to here is what's important. And when that is aligned to that, then that means this is aligned to that. So that is just one of these things on this particular design which is really janky. I mean, it really is janky. I want to do it better. And so now what I'll do is I'm going to jack this thing up. I have a special jack for it that you can put underneath here that I made to jack the front end up. Pull the wheel and get it all torn down so we can get it down to the point where we can go a little further. It just goes to the cross member of the frame. It has this little bird mouth on it and it swivels. This is just a regular scissor jack. So I just welded a 9/16 bolt on it here. You just crank it. So let me get it jacked up and come back and we'll get this thing going as far as the disassembly goes. All right, I got a jack stand on this side of the frame just to give me some backup, but that ain't gonna go anywhere. It will work fine. So anyway, let's go ahead and go over here. So I want to redo these with 2 bolts. You can't even hardly get a socket on the nuts underneath, and that's what pinches this together. I think what I want to do is when I take this thing out and drop this whole thing down, these bolt in. This guy right here, this cross brace, that's not welded into it. This is bolted in through here with some way I did it, I forgot. We can separate this whole thing. I did it so you can separate it, so it's not all tied together and take one side off or the other. There's a couple problems with that too, I'll show you later, but I really like to just weld these holes up and go with one larger one down the center of it. That's really all that needs. There it goes. Just do it the easy way. All right. All right, we got her. So this is what this axle looks like. I forgot what this feature is for on the regular forks. I don't remember. But it's pretty simple little axle, pretty small. And I believe that's an M10 125 thread pitch at the end, so that's not a big deal to make. And we know that this is the part that's sticking out. I can always shove it back in and decide on what to make for a new one, how to make another one, because what I ultimately want to do is I want to have this come out. So when this thing tightens up on the end, it's not only bringing this shoulder on the new one in to the spacers and pulling them all together, but it's also just touching this outside. That way it'll be aligned properly for the brake, and then we'll be able to put it back on and re-weld it, do a better job. So anyway, that's what we're going to do right now. We're going to go ahead and get the wheel out, set everything aside, clean up a little bit, and then we're going to make some measurements to start working on this axle. I'll show you what we're going to use for it. Here's the material we are going to make this new axle out of, which is another axle, just a bigger one. Chrome alley material, whatever it is, good stuff for this. It had a hole in the end of it, as you typically see from these type that you just tighten a nut up on one end of the swing arm. This is a rear axle, obviously. And then you put like a screwdriver through to hold it still. Well, I'm going to make this into the hex. So what I ended up doing was I just measured that, and then turned down a piece of steel, just scrap steel I got laying around, and then pressed it in with the at the vise first with some Loctite 640 on it, and kind of finished it up, or semi-finished it up on the press, and then went back over to the vise and just banged it in with the ball peen hammer the rest of the way, and then just turned it lightly. I don't know what the final size of this is going to be yet, because I need to turn this to what the final size of whatever size fastener, like M21 or M19 or something, probably 19 mil or something will make, and this will pretty much disappear. But this major diameter is the same as the major diameter on this one right there. So we don't have to worry about that. We just put it in the lathe and polish that up with some emery because it's got a little corrosion on it. And then what we'll end up doing, we flip them around this way. If I put this here, and you can picture as kind of the hex is going to be where that big part is of the head of this one right now. I'm just going to dial this in by leaving this long. So when I cut this back, we'll cut it down the length first that we need. Make it a little bit long so we can trim it off at the end. And then we'll turn this diameter. Then we'll turn that diameter and make the thread. A single point or use a die, I'm not sure. But as far as dialing it in, this can all remain constant. We'll just, and, you know, the entire length of it, we'll just make this shoulder a little longer on this one. And then when we put this in, and I have the hex already done, we'll tighten it up. And if it bottoms out on the spacers first, before it hits on that square tubing, all we have to do is cut a little bit away from this, make that shoulder back a little bit so it goes in further. Bob's your uncle, it's done. So that'll be a really easy way to dial it in. I was kind of worried about how I was going to do that. But then when I saw this, I said, wait a minute, that'll be pretty easy. So we'll just make appropriate hex, like I said, and do all this another day, because today is the end of the day, so we'll pick it up tomorrow or the next day. Tis the next day, and we're going to go ahead and make this new axle bolt. I cut it down to length in the bandsaw. I was thinking to myself last night, I'm like, wonder if this thing's going to fit into the spindle, you know, because this end is so big, said the wife. And it does. All right, so we got the center in here ready to go. Put a little pressure on her. Tighten up the jaws. I'm going to indicate it to make sure that this thing is running true, because, you know, it's not critical, but you know me, I like precision. I say that'll do. Yeah, we're within a thou. Actually, I'm going to go ahead and clean this up first. I'm going to clean this face up a little bit, because I don't know how true it is to the shaft. You said shaft. And then we'll take it from there and then measure out. Just use the DRO to back out the 1.465 plus about 60 thou. $1.465, and then we'll go another 60 thou right there. That should be perfectly fine to do what we got to do. I changed my mind and went 100 thou back. I want to make sure I have plenty of material to do this with. We'll use the calipers to start off with, because this has got to be pretty much dead nut. This goes through the bearings and the front wheel. But we'll get it roughed in this way. So it's 787 thou. And we want to go to 589, 590. We touch off and then we'll let the DRO take us in. We'll plug that into the DRO. So this is how this works on these DROs, pretty damn cool. I go to the calculator function and I'd put in 0.787 minus 0.590 equals 197 thou. Sorry about the glare. And then divide that by 2, because we're taking it off both sides. So we want one side. Divided by 2 is 98 thou. So we got to take 98 thou off of one side to get to where we want. Then we come over here and go X, and we got 98 thou sitting on the X axis. We're already touched off. That's the axis I choose for the cross slide. So all we got to do is bring her to 0. We're going to be there, which is pretty slick. A little too fast on the feed. There we go. Try that. Nope. I was afraid of that. Let's run 800 RPM and see what happens. A little better. I don't like this either. I'm going to reset up and do something differently. I don't like that either. I'm not sure if this is like, I wouldn't say it's 4140, some sort of chrome moly or something they make these things out of. So hang on, let me get back on it. Well, it's been a little bit better. I actually got to increase the feed a little bit, but I really need flood coolant for something like this with this kind of material. Let's try a little cutting oil, see what happens. Usually that doesn't help. Just makes a big mess. Not bad. At least it's breaking a chip somewhat. Obviously, I'll do the shoulder. I'm just coming up close to the witness mark. We'll do the shoulder later. I mean, the surface finish is pretty righteous. Anyway, I'm going to go ahead and off camera just whip this down, or either that or I'll put you on a time warp. Got a little side project because we've got 3 thou taper to this shaft. 667 there, 670. We got 3 thou taper. And again, the back is big. So what happens with this is it's cutting big at the back end. Okay, that means that it's set up where the tailstock is too far that way. So it's allowing it to be larger, but when it comes closer to the spindle, it gets smaller because, of course, this is further away. Ergo, it gets bigger. So what happens is this tailstock needs to move toward us, toward me, by 1.5 thou to compensate for that. Remember, it's always on the side when you're dealing with a lathe. So off camera, I'm going to adjust that, and then we'll come back to see where we're at. Inside 625, or 624 actually, 624.5. This is 631. What in the hell? I don't know why that could have gone bigger, because I moved the tailstock toward me, so it should be cutting more. Because we're getting close. 590 is our final dimension, so we got 30 thou to play with to correct this. So I'll probably take 10 thou passes. I'm going to do it off camera. It's going to take a little while to do, and then we'll come back and I'll show you the result. Alright, so here's where I goofed up. And remember before I said, I'm sure I made a mistake somewhere? Well, I did. When I moved the tailstock, I actually pushed it that way. The way this works is these screws, there's one on each side, and there's a lock on the back. This is kind of like a ways, going sideways for the tailstock. I assume that when you tighten these on an opposite side, it pushes it that way. These actually pull it towards you. So in this case, what we want to do is, I'm almost there, but I want to move it another thou. So in this case, if I do this, and I'm pulling this side, I'm going positive on the indicator, which means it's coming toward me. So there's a thou right there. So that was my mistake, and I just forgot about it because I did initially set this when I got the lathe. But you know, this needs to be done periodically anyway. Then you just set the other one to tighten it up, essentially capture it, and then you set the lock on the back, and everything's good. So we're still about a thou. All right, let's get back to it. See, we're getting real close to final. 603.5, 60, just under 603. 603, just a skosh more than 603, maybe 3/10. And this is about maybe 3/10 under. So it's about 6/10 off. I think that's going to be close enough for us because we can dial it in with some emery, you know, because we're going to test fit it, you know. And I think that's close enough. It's well within a thou. I'm not going to try to move this around anymore. So I'm going to bring her down to final dimension and I'll come back. Okie doke, I did a little test cutting on this end because we got to cut it down for threads anyway. And through a little T&A, trial and error, we're at just about 1.5 thou over because I want to take the rest of it down with emery anyway. Oh yeah, you know, let's check for taper. We didn't do that, but it may be to size like at this end. No, it's about 1 thou over there, and this is the area where I did my final test cut, and about 1 thou. This thing ain't got more than 1/2 thou of taper in it now, which is perfect too. Okay, here we go. Looks pretty good. We're walking over to the wheel now. I'm gonna shove it in. I'm gonna shove it in and see how tight it is. Or maybe it's not tight. All right. Oh yeah, it fits good. Virtually no play. It's a nice sliding fit in those bearings and that spacer between the two bearings. So next thing we're going to do is cut some threads on the end. I haven't decided whether I'm going to do single point or a die. I may have single point it and follow with a die because the material is pretty hard. I thought I had an M12 die. Well, I do have one, but it's a 1.5 thread pitch. I thought this was M10. This is an M12 1.25. That's what this guy is right there. I'm kind of guessing as to the length because this is a little longer and it's going to get pushed in a little further when we adjust that shoulder. I got to make sure I have enough threads. So I'm just going, I don't know, a little bit longer than what it is right now. I actually may even go a little bit more than this. Again, this is kind of a guess. I've got really no way to figure it out because I can't put it in and you know, go through the threads. Besides, there's no wheel in between them. So what good is that going to do? So anyway, we're just going to guess and start and end it here. I had to change the change gears around though, which you know, was a little funky setup because I need to go to a 1.25 thread pitch. So I had to change these gears around. That means my feeds are going to be a little bit funky because now I got metric gears in there. So I'm going to have to play with that a little bit. But we need to turn this down to this point that I have it set at on the Z-axis toward the spindle to 471 thou imperial, which is the major diameter for an M12. Based on the DRO, what it says, we got to take off just under 60 thou to reach it. I'm just going to buzz through this. There we go. Need to speed that up too. Let's speed that RPM up. What the hell am I at? Oh shit, I'm at 600 RPM. Doi! Now I'm on 0 on the DRO. It should be dead nuts. Yeah, 470, close enough. Then thou is fine. All right, so I'll set up for threading. For you folks across the pond, other parts of the world that don't use bananas, major diameter that I just turned that to in imperial is 0.471 or 11.972 millimeters. That's the major diameter for an M12. And then the minor diameter for an M12, in other words, that'll be the root of the thread depth, is 10.305 millimeters or 0.405 according to the chart I found on online. That's 405 thousandths imperial. That means if you take that total amount and divide by 2, you got 33 thou or 0.838 millimeter for a thread depth approximately. So we'll get close to that. I'm not going to use the compound. There's no reason to use a compound at all on this. You don't need to advance in the 29.5 degrees. It's really you only need to do that when you're doing a really heavy thread, deep threads, not even with this type of a cutter, with a full form cutter, and just puts the tool load on one side. We're only doing an M12 1.25 thread pitch. It's like nothing. So I also squared the tool off with 123 block. I'm going to slow my speed down to about 220 to start with. Do some bluing, say 3B, and then we'll, come on, there we go. See how that looks? About right. Let's go ahead and do that. I'll just chamfer the end real quick, but I'm going to put a bigger chamfer on it when we get done because I don't know what the length of that's going to be. I made a boo-boo. So I'll do that here in a sec, but I wanted to talk briefly about these metric threads on these machines. Technically, you can't disengage the thread engagement. You have to leave it engaged. So you go forward, don't disengage, just kill the lathe as far as the spindle goes. Unfortunately, there is some spooling, so it continues to go a little bit. I don't have a spindle break on this one, in other words. And then you reverse the lathe and come back, advance your tool in, and then repeat, rinse and repeat. There is a way to do it to disengage. I'll show it to you some other time, but there's a couple of good videos. Max Grant has got one. It's an older video, probably 6 months old or so, where essentially you disengage, but when you come back, you re-engage on the same number you disengaged on. So you essentially go forward and come back. You just don't let this thread dial go around one time. But we're not going to worry about that because we don't really have a shoulder we're going to go up against. So when we get really close to this, I'm just going to spin the cross slide out real fast and get the clearance, and then so I can have my finger on this to go forward. And when I get to that point, I just kind of just take it and whiz this thing out as far as this goes. So if I was going to simulate it here, back the tool off a little bit, I would essentially have it in threading, which we're going to do right now. I don't have the selector right yet, but you get my drift. Now we're in threading. So if we were going to thread, so what you do is you engage the half nut, which is engaged right now. I don't know what thread pitch this is. We're just kind of demonstrating. I'll use the button over here, where this, hello, where that little hand is, big hand, and then we'll hit this. Just advance the thread that way. We're actually going to be cutting this way. And then when it gets up to where we need it to go, we just release it and back out really quick like that. Hopefully we don't smash the tool. So that's one way to do it. I'm going to disengage now. Let me go ahead and set the thread in the gearbox, and then we'll start. We're just going to do a scratch pass. There we go. So we'll get right up to there. Try to get a little closer once we get our jive in. And we'll go backwards. See what we got. I'll do the chamfer on that later. I don't feel like disengaging now because I've already scratched past it. We got to leave it here now. 1.25 thread pitch. Yep, looks right. Okay. Oh, what the? I keep breaking inserts. This is my third one. I've rotated this around to the third side. I have no idea what's going on. The tool's on center. It's squared off. I'm going to try 200 RPM instead of 220 because this stuff is awfully hard. Maybe it just doesn't like that speed. That's better. That's a lot better. I just didn't like that speed for some reason. I don't know why. All right, I found me an M12 nut. It's a Teflon nut, so it's not going to go on all the way before it hits that, but it starts to go on perfectly. I mean, that's a nice thread right there. I didn't go to 33. I went to 28 thou and did a spring pass and then tried it because the peaks of the thread were really forming. I figured that was going to be right. So we're going to go ahead and disengage. Now we can operate the carriage freely. I really should have chamfered this before. That was dumb not to do that. I'm going to put a different tool in and give it a nice chamfer because that's probably what contributed to breaking these insert tips. But when I slowed it down to 200, it worked perfect. So I think we're looking good. Okay, we're over back in the disaster zone, and here is the finished product, or at least semi-finished product, because I think we're going to have to dial in that shoulder. But what I ended up doing was I put this in an ER32 collet, and I cut this down for 24 millimeters. A 24 mil wrench fits perfectly over it. There's not a lot of shoulder left, but there doesn't need to be. I actually may end up putting a stainless washer on it and then calculating that into the whole thing before I cut this back. You know, once I get everything back together, we see how far it pulls in. And then figure that out because I think it'll be a little bit better with a washer. But this is not a tightening point. This is just a register. So what this will do is, it goes in from this side, of course. All right, this will keep this side from moving outwards to keep the brake caliper in line with the rotor. What keeps it from moving inwards is the fact that it pinches down, which I want to redo this as well, as I said before. I think I want to take this out, and I'm going to weld those holes up, and maybe if the bottom is flat enough, I'll put it on the mill, and we'll just put a single hole through it for a little bit of a larger bolt. That'll be fine. Get that out of there, because that's dumb. And then that pinching of this, essentially it pinches this, and it pinches the collar because these are two different sizes. That's why I didn't make the shoulder longer. I could have made the shoulder long enough to go straight through and go up against the wheel itself, the bearing, where this spacer goes, right? The way I designed this, the spacer is larger than that, and so this hole is bigger than this hole. So I got to keep it the way that is. So this is going to bump up against here like this. You can see the spacer up against it. And this part there, because the holes are accommodating this side and that side, will pinch on both of them. And that'll keep it from moving inboard. So this part keeps it from moving outboard, the little flange there. And then the pinching will keep it from moving inboard and just keep that caliper aligned with the rotor. And then speaking of that, of course, I need to cut all this off, as I said before, grind it down. I'm going to clean all these welds up. These welds, they just look terrible. And I'll grind it off, maybe re-weld some stuff if I grind too much off. But I just want to clean this up and make it look a lot better and make it more functional, because you can see here, here's your movement in this right one. You see this right one moving pretty good. A lot of play in that one. What limits that is when you tighten these down, which is not the way to do it. So this one's pretty tight and it'll hold itself up like that. But the way to do it is to make sure that we have a good precision bore through here. I'm going to use a larger fastener, and I think what I'm going to try to do is, and this will be in the next video, and maybe line bore that through on the mill. So we just cut everything through, straight through, nice and concentric and straight relative to the sides of these guys, because I went off of that originally anyway. And then just use a larger bolt. I'm not really sure what size that's going to be, because there's a hell of a lot of meat in here. There's plenty of meat. I actually have a, there is, the hole is actually a little bit bigger inside here anyway, because there's a sleeve. And I drilled holes in the sleeve because there's a grease fitting on the back side here. You just can't see it. So there's holes in the sleeve so the grease can get between the sleeve and the bolt. But it's all the same material. It's all steel. So it works up to this point, but it's just sloppy. I don't like it. So we already have that inside bigger. So we can just essentially bore it true to whatever the bolt size we need to go up to, and don't worry about a sleeve. It's not going to be necessary anyway. I think I did that because it was the only thing I could get. There's like an outer sleeve and an inner sleeve, but the tolerances on those are pretty crappy anyway, the two commercially available sleeves. I mean, the tolerances are like a hot dog down a hallway, so that's why it's like this. So that's what we're going to do. I'm going to try to do that, and again in the next video, and try to figure out if we can line bore that with the boring head on the mill. Clean that up and figure out what bolt we're going to put through. If we can do that, then this is going to be really good, nice and tight and a lot better. And I think it'll be a lot more functional too, and it'll look a hell of a lot better when we clean all this crap up. So that'll be it on this first video. So we saw some disassembly. I told you my objectives. The next video, we're going to be working on these arms, and we'll see what we can come up with. I'm not 100% sure I'm going to be able to do it the way I want to do it, but I'm going to give it my best try. And that's what you'll see on the next video. So if you want to see that, you need to stick around. You know what you need to do. Ring the bell, share it with your friends, like, subscribe. I already said ring the bell. Subscribe. Do all that stuff. You get notified when I put more stuff up on this job and other jobs, anything that might come in. Well, anyway, as always, don't just repair, restore. Thanks for watching, and we'll catch you on the next video.